Hello everyone, welcome to the Thinking in Real Analysis series. In these videos, I hope to cover some basic analysis proofs and the canonical techniques used in them. To start, today we'll be proving that root 3 is irrational, which is a classic proof in analysis. We're not doing root 2 since that's a little too classic, but this proof will hopefully generalize the basic framework for showing irrationality. Alright, let's get started. Now, most proofs in math hinge on some important definition. However, the issue we run into here is that we don't really have a good definition for irrational. A classic approach here is to use contradiction, since this will give us some structure that we can work with. So let's suppose that root 3 is actually rational for the sake of contradiction. Now we have a definition of rationals that we can actually work with. That is, root 3 equals p over q, where p and q are integers, q is non-zero so that we don't divide by 0, and p and q are both in lowest terms. The former statement is pretty important since that is what we will try to contradict, and it simply means that p and q have no common factors. Now let's square both sides of this equation and get rid of the square root. And we get that 3 equals p squared over q squared. Then let's move the q squared over and we get that 3q squared equals pq squared. We're trying to contradict the fact that p and q are in lowest terms. So let's go ahead and try to find a possible common factor for both integers. One way to do this is to realize that this equation says that p squared is divisible by 3. Now intuitively, if p squared is divisible by 3, which is prime, then it makes sense that p will also be divisible by 3. How do we prove this? Well, one way is to use Euclid's lemma, which says the following. However, let's try to do this directly without using any theorems from number theory. We want to show that if p squared is divisible by 3, then p is also divisible by 3. Let's approach this with a contrapositive, since again, that gives us more structure and allows us to work with p instead of p squared. Now we want to show that if p is not divisible by 3, then p squared is also not divisible by 3. If p is not divisible by 3, then we have two cases. The first one is p is 1 more than a multiple of 3, so we can write p equals 3k plus 1. If we square this, we get the following. And then we can factor out another 3, which tells us that p squared is also 1 more than a multiple of 3, so it cannot be divisible by 3. In the second case, p is 2 more than a multiple of 3, or p equals 3k plus 2. Again, when we square this, we get this. And if we rewrite it as so, we can again write p squared as 1 more than a multiple of 3. Which means it cannot be divisible by 3. Hence, we have shown that if p isn't divisible by 3, then p squared is also not divisible by 3, which by the contrapositive proves the statement that if p squared is divisible by 3, then so is p. Now we can write p as 3n since we know it is divisible by 3, and then we can substitute this into our equation in question. We now get that 3q squared equals 9n squared, which simplifies to q squared equals 3n squared. But this equation now tells us that q squared is divisible by 3, which we know means that q must also be divisible by 3. Hence both p and q are divisible by 3, which contradicts our initial assumption about rational numbers. And that's it. Root 3 then must be irrational. This isn't the most satisfying proof. However, it illustrates the idea of using contradiction and contrapositive to prove statement when there isn't much structure to work with. That is all for today. I will see you in the next video where we will prove a statement about supremums.